Right. Can someone tell me which, is it left or right swipe? Which is the one when you want to, when you want to, oh, never mind. I think that was a do. Oh, anyway, here, I'll put that down. Should I get to class? Well, I want to welcome you all to the special COVID edition of 344 or 346. Actually, I don't remember. But here we are, and we're going to have to do things this way on YouTube, probably the whole semester. They said to me that there's some chance they'll open the classrooms back up before the end of the semester, but I really doubt it. So here we are. I'm going to do as much as I can to make these videos watchable, improve the sound. I'm going to be doing some video effects. So like today, if I have some data on the board, I'm going to overlay that with an image so that you can read it as easy as possible. We have a crack team of videographers who handle all the digital effects. So we're going to do that to make this as workable as possible. Not enjoyable. No, we're not going to enjoy it. But we're going to make it as easy as we possibly can if we can't be in here. So I'm also not going to lecture the entire time because normally we'd have a little bit of questions, which we're going to do during office hours. So I'll try to keep the lecture down to about 45 minutes. With that said, let's see, I've already sent you something. If you didn't get my email, I sent you all a PowerPoint with all the class policies, so I'm considering that part finished. And so we're going to go ahead and start straight up lecturing as of right now. The only other thing I can tell you is, in this first part, we have 2 weeks of a material that's called Maxwell-Boltzmann, and I can't really find that. It's not in your current textbook. And there's only one textbook that I know that it's in, which is weird because you almost always cover this material for 344. Again, it's Maxwell-Boltzmann. Now, because of that, I've already told you, I'm working on my own textbook. It's just not done yet. The chapter 11, which is Maxwell-Boltzmann, that mostly is done. So we can work with that. And then there's one more time where there's a subject that I don't think that your book covers. And I didn't want you to buy a new book. So that I have just now started writing the chapter in this free textbook that I have. Look, it's not great, but the price is right. So there you go. It's the best I could do. One thing you'll find, and I hope a lot of you go to grad school, is that when you get to this top level, I mean, we're right at the level of grad school, right? This is the last class. When you get to this level, and you get into grad school, there's no good textbooks. That's why I'm trying to write one. And it's weird, but it's true. And that's because, especially at an undergrad level, they're making these textbooks to make money, not to actually teach you anything. So sometimes those don't work together. So sometimes the textbooks are sometimes they can be a little too simplified, and that's kind of your case right now. So sometimes they're missing subjects. So what I'm doing with my free textbook, it's going to be like 600 pages. And what an instructor can do is just choose to or not to use parts of it, right? But because I'm not trying to make any money off of it, I literally can't. I have a contract with the university. Because I'm not making any money off of it, I'm not designing it for that purpose. I'm just filling it full of information. And we're going to cover the parts that we need to cover. Anyway, with that said, why don't we go ahead and just get into it. So, my handwriting isn't too bad. It's not perfect. And when I go off the rails, I will use digital enhancements, or when I'm trying to do figures or a table. I have a table today. I'll do some digital on that to make it readable. There will occasionally be mistakes, a factor of 2 missing. Again, I try to digitally overwrite that when I make those mistakes, but I'm not going to do it perfectly. Tell me if I do that. You figure it out after the fact. Again, today's subject is Maxwell-Boltzmann. And I will tell you who these people are when we broach their contributions. What happens is like this guy came up with the underlying theory that this guy did like derivations, like made it more specific for what we're doing. So that's why both of these guys get their names on it. I need to spell it all out perfectly or the world will explode. So we're going to cover we're starting with Maxwell-Boltzmann distributions. there's two things about this. In the big picture, Maxwell-Boltzmann and this whole class, which is mostly quantum mechanics, is about probability. The mathematics of probability. How do you use probability to study, if we're going to choose chemical phenomenon, because remember, you were the one who signed up to be a chem major, right? So there you are. So we're going to use probability to understand chemical phenomena, and that includes quantum mechanics, which is most of what this class is. Maxwell-Boltzmann is not quantum, but it has a lot of elements of quantum. It's a good warm-up. Really, you're going to want to do this, because if we go straight into quantum, that's going to suck for you. I mean, you're immediately in over your head. And you're going to see what I mean here in a minute. Let's see, now what else do I want to say? So yeah, that's the theme of the class, and it's also a good warm-up for your mathematics. We're going to be doing things with calculus that you never were exposed to before. And cool, right? The problem is that sometimes you psych yourself out into thinking that you don't know what you know. What's the integral of 1 over x? Oh, it's natural log of x. Well, what's the integral of 1 over volume? I don't know. Well, you should. It's natural log of volume, and you should have covered that last semester. So, again, when things are unfamiliar to you, you think that I don't actually know anything, and you actually know everything. It's just not familiar. So we're going to build up our math muscles with Maxwell-Boltzmann so that we're ready for quantum. Anyway, that's the big picture. Now, I promised you that we're going to start easy. Quantum sounds fearsome, doesn't it? It actually is. But anyway, we're going to take baby steps. First baby step is a coin, right? It's all about probability. Quantum, this is about probability. I'm already talking about flipping a coin. Quantum is also probability. All right, so I'm talking about flipping a coin, but the coin is actually a molecule. All right, so let's make the coin a molecule. All right, so what about this molecule? Well, it has two sides. And what I want to do is flip this molecule, and I'm going to make an observation, whether it's heads or tails. And what I want to know is that the molecule is a head and tail molecule. That the molecule has two sides. Maybe that's like two conformations, whatever. Anyway, you get the point. Two sides. And the way to know this is to experimentally probe it. And to do that, of course, I'm going to be flipping it over. Anyway, I'm going to flip it over and over again. It's also important to come prepared. I'm going to flip it over and over again and look at the results and try to conclude, because I already know the answer, that this molecule has two sides. Now, at this point, hopefully you're thinking, whoa, this is actually going to be like childishly simple. All right, just give me a minute. Okay, now if I'm going to see that there's two sides to this coin molecule, I got to do two flips. Now that's obvious, right? So flip 2 times, and what can I get? Okay, that's kind of obvious, right? Heads. Now the odds of that are 25%, right? That's kind of obvious. So I'll just write that down, 25%. Okay, kind of bad because what I really want to see is a head-tail, or a tail-head, right? Because there's two sides. That's my point. That's what I'm trying to figure out, that there's two sides to this molecule. That's not helping. Now, and also, let me just remind you what all the possibilities are. And how did I know it was that heads was 25%? I knew that heads was 25% because that is 1 out of 4 possibilities, right? Heads, tails. 4 possibilities, that's one of them. 1 out of 4 odds of observing heads, 25% probability, right? And again, I told you this would be really easy. Okay, so middle school level math. All right, now here, I have a 50% chance of observing the head-tail or tail-head and correctly surmising that this molecule has two sides, right? So I see that and I figure it out. Again, middle school students would know this. Now, let me throw a monkey wrench into this, because let me remind you that when we do observations in chemistry, physics, whatever, I have like some kind of gas chamber, and maybe I'll digital in some kind of gas chamber like Non-Jang has or Mike Trineri has in our department. some kind of gas chamber, right? And I have lasers going into it. So I'm observing not one or two molecules. I'm observing, around a mole, maybe more like a tenth of a mole. That's actually pretty accurate. Tenth of a mole is about the size of a balloon. Okay, that's a lot of gas molecules. That's a lot of coins. So here's the part where I'm going to throw you off from what you think you know. And I'm going to start looking at statistics as a function of number of coins. And I will digital in a table here, but I'm going to have to start writing things at first. And again, my handwriting may not be super great, so that's why I'll digital put in a table once I'm done writing it. It's in the textbook too. I wrote the textbook, that's why. Okay, so 2 coins. And what I'm saying is that I need to see tails, heads, or heads, tails. In other words, I got to have an exact 50-50 split. Half the flips need to be one, and the other half have to be the other, exactly half, or I don't surmise that there are 2 perfectly even sides to the coin molecule, right? So here you go. All right, now, we've already covered that 2. It's, again, our middle school math tells us that the odds of observing tails, heads, tails is 50-50. Okay, not bad. But now again, I told you that this is actually going to get oddly more complicated. I'm going to do 60. There's 60 of you enrolled in this class. That's why I picked 60, by the way. There's always 60 people in the class anyway. 60 coins, or 60 flips of the same coin. Let's say that there's 60 coins. That's more realistic. I want to see 50 tails and 50 heads, exactly 60. I want to see exactly 30. What did I just say? I got to edit that. I want to see exactly 30 tails and exactly 30 heads. Perfect. Not 29 tails and 31 heads. 30 tails, 30 heads. It must be perfect because the coin is perfect. It has perfectly even size. Now the odds that I'm going to see exactly 30 tails and 30 heads, no, I'm fixated on anyway. The odds that I'm going to see exactly 30 tails and 30 heads is 10.4%. I used a computer to figure this out. So I have 60 molecules. If I study them, I only have a 10% chance of observing that they are perfectly even-sided. That there's 2 sides and they're perfectly even, only a 10% chance. And guess what? It's going to get worse. Let's do 600. Okay. What are the odds that I get exactly 300 heads and 300 tails? Not 301 and 299, 300, 300. One other. The odds are 3.51% that I make an observation of 600 coin molecules and I see an even split. That's not good. Just for the heck of it, let's go to 6,000. And of course, 3,000 heads, 3,000 tails is pretty unlikely. It's only a 1% chance I would observe that. But let's go all the way to 1 million. And the odds of observing exactly 500,000 heads and 500,000 tails is 0.13%. Pretty bad. Now, remember how many coin molecules I'm actually observing? It's around a tenth of a mole, so that's 10 to the 23. Now, how do you think this is going to go when I get down to 10 to the 23? I couldn't even calculate it. Actually, I could, but anyway, it's a really, really small number. You thought the flip of a coin was going to be real easy. It turns out that when you have so many of them, it actually gets obscure. And when we're studying molecules, we have many of them. So it seems like we have a bit of a problem here, don't we? Now, of course, there's a solution, or we would be talking about it. In fact, I'd just be drooling on myself. I am getting kind of old. And the answer is that obviously, the problem is that I'm being very bullheaded about saying I have to have 500,000 heads and 500,000 tails. I'm not giving myself any wiggle room. Now, that's stupid. That's just plain stupid. I need to give myself a little bit of leeway for the fact that even a perfect coin isn't going to just evenly divide whether it's heads or tails. I mean, you just know that, right? Okay, so now to make sense out of what I just said, here's what I'm going to do. I'm going to ask, what is the percent chance that I'm going to get a 50 plus or minus some kind of wiggle room split? And then I'm going to write down the probability that that happens. Okay, so what does that mean? Okay, we don't need to worry about 2 because that's kind of childish. The problem is when we're talking about really big numbers. Okay, so now let me explain what I mean. We'll start with 60. So what I'm going to say is I'm going to allow myself a 50% observation window plus or minus 15%. So what I mean by that is, here, I need to make that bigger. Okay, here's what I mean. Previously, I decided that I had to have 30 heads and 30 tails. And if I saw that, I conclude that the molecule is two-sided and the sides are even. That is perfectly reasonable. I mean, of course. However, it's not practical. So, and I'm not likely to observe that, so this is stupid. Instead, what I'm going to do is I'm going to give myself wiggle room. Now, what this means is that I decide that the coin molecule has 2 even sides if I observe between 21 and 39 heads, and then 60 minus that tails. Obviously, you would get that. So I don't have to have exactly 30, I just have to have between 21 and 39 of one or the other. And if I see that, then I'm going to go ahead and say, well, that's actually a two-sided molecule, 2 even-sided molecule. And if I do that, how many times would I observe heads, tails that follow that range of 21 to 39, a head or tail? You would observe that in 48% of the flips. There's your 50-50. Now, it's not perfect, right? But it's close. So now I'm starting to see the 50-50 nature of the coins that I was able to see with 2, and I need 2 because there's heads and tails. 60, it got obscured, but now I'm seeing a way to see that even sides, that 50-50 nature of the coin is now starting to come out. I just don't analyze it like stupidly. Now let me go further with that. Okay, for 600, 50 plus or minus 9%. So again, I don't say that I have to observe exactly 300 heads and corresponding tails. I give myself a little bit of a range. It doesn't have to be that wide, just 9%. But if I do that, I decide that the molecule has an even-sided heads, tails. And if I give myself that wiggle room and I do a bunch of coin flips, which I did a simulation on a computer, I see that happen 49% of the flips come out with heads, tails, 300 plus or minus about 30. Right? Within the wiggle room, half the time I see heads, tails within the wiggle room, making it clear that this is a two-sided coin. Let's go a little further. Okay, it's kind of stupid at this point. Let me just write down the numbers just because I started writing all this. Let me just finish it. 6,000. What are if you have between 2,820 to 3,180 heads, and correspondingly that 6,000 minus that tails, you would observe that 51% of the time. And as you can imagine, that as I get to a really high number, the spread actually gets way smaller. The spread is now 0.226. You have to have a spread, but it can actually be really small. Look at that. So if I give myself just a little wiggle room, I will observe an even split with a wiggle room 50% of the time. And that makes me conclude that the coin has, right, there's the 2 sides of the coin. There's the 50-50, right? It's just that I couldn't analyze it in such a straightforward manner. So there you go. And hopefully I'm doing the digital, so you can stop and write it down. I believe this is also in your textbook. I haven't looked at it in a while, so I'm not sure. But anyway, so there you go. You just can't analyze it the same way, which is the point. All right. So again, this is not too hard to understand. The analogy here is that when we're looking at our little reactor system, our gas phase spectrometer has probably around 10 to the 23 molecules in there, and there you go. So we see we have to do some analysis of probability that's not quite like what we learned in middle school. That's why you're a senior chemistry major, about to get a college degree. How does this work? All right, now I'm going to start indoctrinating you in how to correctly analyze things with probability. Maybe you've had this in a math class, but I don't presume that, right? Okay, so here's probability. Okay, the 50-50 part that a child understands. All right, where do I get this? Because I can't do it this way. How do I use this? How do I turn this into like an equation that I can always just put things into and get good answers out? How do I do that? It works like this. This is me telling you how it works. I can't really derive this. I'm just going to tell you, like, this is how it works. And this is how it works is you get to this thing. This is called a probability density times the spread. Okay, so probability density would be like the 50%. The spread is the spread, just like I did before. So you see how that works. Probability is the thing you understand as a child. A coin has a head and a tail, 50-50 that you observe one or the other. Okay, so obviously we have to understand exactly how this thing called probability density, which you probably most of you have not seen this before. Now we have to know how this works. All right, now to do that, there's a couple of details. We have to go through the details and figure out what we do about them. Now, detail number one is that the spread is dropping. We are using probability density because we are going to be making observations on very large numbers of molecules, because how can we not? When I'm doing that, I see this formula, which you have to accept as a given. Trust me, it's true. But the spread keeps getting smaller. So notice that as n increases, you'll get used to my shorthand. As n increases, the spread drops. Okay, it drops how much? Actually, it goes to basically 0. And by 0, I mean partial, right? Partials in calculus are basically 0. So as n increases, the way this works is that you're now getting something that looks more like this. Okay, now I never said what y was. Y is the observable. So here, let me write that down. Y is the observable. Now, how to say mathematically that y is a coin flip is, I don't know, that's weird. Mathematically, how do you express a function that is, what, 0 or 1? Yeah, it can be done, but you know what? Let's go ahead and drop the coin thing. Let's say it's energy. Why not, right? So now let's go ahead and start walking into the world of chemical this or that. It's energy. I know what energy is. You just had a class on energy. All right, and of course, energy has units of joules. All right, so what? Okay, there's a couple of things here. Let's see here. Remember that a partial is basically 0. This is terribly important. Hopefully you learned this last semester. Partials have units. So this partial, if y is our observable is going to be energy instead of heads or tails, if it's energy, the partial is 0, right? It has 0 width. If you think of these as like integrals as like areas, this is like the width, and it's infinitely small, but it does have units. Now, you may have noticed that I just said the nasty word integral. All right. I've got my probability density that we're still working on understanding. I told you that it exists. I haven't told you what it is yet, so don't be frustrated. I'm focused on this right now. This is basically 0. And 0 times whatever is 0. This is useless. Now, I've already talked about y. the delta y is actually partial because you can see that trig right here with our spread. But when you have very large numbers, the partial of y is 0. And 0 times anything is 0. That makes this useless. In fact, all mathematical expressions with partials, with just a partial, is useless. It's 0. To make a partial useful, you either divide it by another partial, which is a derivative, or you integrate it. Okay, so guess what? We can now understand the two sides of a coin by making a large observation. We just need to know what the probability distribution is, and then we're going to have to integrate it. So that's what we've gotten so far, which is pretty good. Actually, that's kind of awesome. Yeah, we can go home now. No, I'm just kidding. We have 45 hours of class, by the way, so we have exactly 44 and 40 minutes left of hours before we're done. Okay. Of course, this is integrated as probability. All right. Next thing. If I'm going to do, I'm going to describe the probability distribution, like the mathematical form. It's like e to the energy. I'm going to do that in a few minutes. We're getting there. Now that I have an integral, I want to make sure I know how to do the integral. Little steps. All right. So what do I mean by that? All right, an integral. Let's talk about the probability that a molecule has a certain energy E. Okay, now again, let's integrate a probability distribution. I'll just call that P. Our observable is E, and of course my partial is a partial of E. Okay, now the thing that all integrals require are limits, so this is my point. We have to have a lower limit, a lower energy, and you have to have an upper or a high energy. All right, what are those? This, by the way, is a big deal. Make a little star by this. Limits of these probability distribution integrals, that is something that you're going to be tested on. Let me make it that clear. I'm going to test you on it, so it's a big deal. All right, now, to try to, again, understand the nature of this thing, I want to put some numbers in and see what comes out. That's a good way to, it's like an experiment, right? Experiment with math. What would be a good lower, you know what lower energy is? You can't have negative energies, by the way. No, you can't do that. So let's say that the lowest energy is 0. Now that's fair. Okay. What's the upper energy? The upper energy that a thing could ever have would be infinity joules. Now, the universe is finite, so there is not an infinite amount of energy in the universe, according to physicists, whatever. I think it's a good enough approximation to say that there is a lot of energy that's kind of close to infinity. So what I've done is I've covered all my bases. Definitely you cannot have less than 0. Doesn't make sense. And infinity is a little bit of an approximation, but probably not a bad one. Okay, now I'm integrating over all the possible energies that this molecule could have. So probability distribution, I haven't defined it yet. But I know when I integrated it, and I'm integrating over all possibilities, what do I get? Now again, you should not know this, but if you could guess the answer, that's great. You get 1.0. 1.0. Now, probability speak, I hope you know this. When you are talking about probability and you're not in middle school and you say 1, you mean 100%. So 1 is 100% in probability world. What does it mean for this integral over all possibilities to integrate to 1? That is called normalization. That's the mathematical word for that, whatever. It means that a molecule has energy, has some energy or no energy at all. So now let me again state that plain spokenly. Either a molecule has energy or no energy. Right? Of course it does. It is 100% probable that a molecule either does or does not have energy. Of course that's true. And in our math speak, we integrate the probability distribution over all possibilities and you better see the number 1. And if you don't see the number 1, you screwed up, which you better look out for that on your test because that's what you're being tested on. And I'm giving away too much. All right. Okay, so tell you what, let's do something else. Let me give another example. Okay, now I need a new board. What am I doing? I'm using the board all screwed up. Anyway, I forgot I was on the other board. All right. Let's say that wherever we see energy, we're going to change things around a bit. Let's plug in kinetic energy. Right, so we have this integral equation integrating the probability distribution as a function of E. But you know what you do? This is really kind of neat. That means therefore. You're not used to E yet, but you will be. So let's integrate 1/2 mv squared. And our partial is now velocity. It's still energy. It's just wherever you see an E, plug in 1/2 mv squared. And now it's the probability distribution of velocity. Now another thing to be careful of. The limits are not 0 to infinity joules. Limits have the units of the partial. We are now in velocity. That means the lower limit would be 0 meters per second. This would be net velocity. You can have negative velocities if you're talking about direction, like Vx, Vy, Vz. Negative directional velocities are for things going backward. Again, that'll be on the test. But I'm talking about net velocity. Net velocity is, of course, the square root of Vx squared plus Vy squared plus Vz squared. So it cannot be negative. That's impossible. Okay, so my lower limit is 0 meters per second, and my upper limit is infinity meters per second. Of course, the answer is 1, just like before. It's normalized. Remember that word? It's normalized because a molecule is either moving or not moving. Ah, we're all geniuses, aren't we? Of course, things are either moving or not moving. It's 100% probable that one or the other is true. So we're getting really good at this mathematical stuff, right? So, yeah, I mean, that's really all it works. This is a walk through probability distributions. Last bit. Let me show you one other thing. Let me show you where probability distribution, where that word comes from. It's kind of obvious. You can always figure this out just by doing what I'm about to show you right here. Okay, so probabilities are like ratios. It's like heads over all possible outcomes, right? When we were talking about flips of a coin, heads was 1 in 4 because that was 1 out of 4 possibilities. Probabilities are ratios. Ratios have no units. It's not a joule, it's not a meter per second, it's nothing. Ratios have no units. All right, velocity, I've just been ripping your head off, is in units of meters per second. If this was energy, it would be in joules. Therefore, the probability distribution has units of 1 over meters per second. So a probability distribution or probability density, the same word for the, 2 different words for the same thing. Be careful of that. I think I put that in the little textbook. There's a lot of that in science, right? The probability distribution or density has units of 1 over what it describes. Let me say that again. The units of a probability distribution or probability density is 1 over whatever it's meant to describe. This is meant to describe velocity, therefore the units are 1 over velocity. And the reason is because of what I've written right here. This is how you use probability distributions. They integrate to something with no units, therefore the units of the partial have to be canceled out. Now you may be thinking like, well, doesn't the integral affect the units? The answer is no, and I just showed you that. And just trust me. I kind of find that weird, but there we are. All right, so that's all I have to say about that. All right, we have done a lot with probability distributions. We know how to use them. although we've been very non-specific. Now, to get specific, like to start like integrating e to the x and all that jazz, which, yes, you're going to be doing a tremendous amount of, I need to show you what the probability distribution function is, which is basically e to the x. All right, probability distribution function for molecules. Now, the way that this works is, the trick is that we have a probability distribution for energy. This guy, the Boltzmann, okay, 1868, Boltzmann, Ludwig Boltzmann. He was most certainly a vampire. In 1868, he figured out the formula for the probability distribution of energy. Now, what do I mean by the probability distribution? What this is how nature distributes energy of all types, for any type of energy, rotational energy, thermal energy, which is mostly translational energy, nuclear energy, quantum energy. There's nothing that can come out of your mouth that nature doesn't distribute, that the probability distribution isn't Boltzmann's formula. And what does that look like? I'll show you. I just want to let you know that when Boltzmann figured it out, awesome. This is important for literally everything, and then he killed himself. Sorry, I know I joke around a lot, but he actually killed himself right after he discovered this. Anyway, all right, now, let me show you what it is, but don't write this down. Do not write this down. I'm going to make a mistake. I'm going to make a mistake so that sometimes mistakes are instructive. All right, so let's say that it was this. Now, again, do not write this down because this is an error. I don't want you writing down an error. All right, probability distribution of E sub I. Now, E sub I means that I'm being very specific. Like, what's the probability that an argon atom has a joule of energy, right? That was very specific. Notice all the very specific things I said. Argon, no degrees of freedom, doesn't vibrate, doesn't rotate, 1 joule of energy, and maybe it's kinetic. It has to be kinetic energy. It doesn't really have any other energy, right? It has nuclear energy. I guess it could build an atomic bomb out of argon. He actually could. It just wouldn't work very well. But we're not in nuclear class, not yet. So I'm going to say it's translational energy because that's really all that I have. Now, the following formula is wrong, but instructive, so do not write this down. But let me tell you what I'm trying to do here. Normally, probability, like heads, tails, blah, blah, works by what's my observable divided by all possible observables, the number of observables, right? There's 1 heads, heads, and there's 4 possibilities. Heads, tails, heads, blah, blah, blah. Okay, so the probability is 1/4. Okay, cool. That works for flipping a coin, but I'm not talking about flipping a coin. I'm talking about the energy of an argon atom. Okay, so this is not right. Just pointing that out. But I do want to point out actually one thing. This is what we call the normalizer. Now, it turns out as much as this is intuitive, and as much as I would like this to be the formula, because look how easy it is. It's just like 1 joule divided by whatever energies it could potentially have otherwise, which we'll define in a minute. But this is not the right formula. The reason is that if nature worked this way, if nature did this, then the problem is that mass and energy itself are not conserved in like chemical reactions and stuff. Well, they are, so this ain't right. Now, this formula I'm going to show you can be derived. And it's kind of hard. I'm not going to do it. It takes all day. So I'm not going to do it. So please accept what I'm going to give you. I don't do this often. I very rarely throw something at you and say accept it. I usually prove things. Of course, where do I start the proof? Let's stop thinking, all right? Let's just write down kind of what the formula looks like. So this is not right. This is closer. This isn't quite right either. So don't write this down either, but it's closer. Okay, it's e to the energy. Again, it's not quite right. I have one more thing to do, but this is close. Is e to the minus energy. This is what Boltzmann kind of came up with. Give me 1 second and I'll write it out for real. All right, and it can be derived. I keep harking on that I keep writing down the wrong formula because, again, it's instructive. What's instructive? This is instructive. Let me write down e to the minus energy in a Taylor series. And I can show you why this is not quite right. Not quite right. We're almost there. Why is it not quite right? Let me write down a Taylor series. 1 minus energy. And you've had Taylor series. So you know this. Over n factorial, dot, dot, dot. Okay. What's wrong with this? No units. Joules. Joules squared. Joules cubed. Here's what's wrong with this formula. In physical science, you cannot have a mathematical expression where things are sum with different units. You cannot do that. Let me give you, when you have trouble understanding, like let's just say like what I just said, like why is that? Think of an extreme example. The number of cats is the temperature plus the miles to Evanston. What? Right, that doesn't make any sense. Why? Temperature plus miles? That doesn't make any sense, right? And for the same reasons, this doesn't make any sense. Remember, subtraction is just the addition of something negative. So I look at this is a sum. Minus signs don't bother me. This is a sum. No units, now I have a unit, now I have a different unit. I mean, squaring a unit technically makes it different, that's fair. Cube of the unit, all of these terms have different units. It's no different than whatever I said before. This is nonsense. This is nonsense. There has never been an equation for anything in physical science, physics, math, whatever, chemistry. There's never been an equation that was correct that looks like this. They all either can have no units or they all have to be joules or whatever. They all have to be the same. So this is wrong. Okay, now let me do it right. The solution to this would be to divide by something that has units of energy. And I'm going to divide by kBT. And I know that's a little small. I'm sorry about that. I need to plan a little bit ahead. Okay. What I've done is I've taken e to the minus energy and I've divided out the energy by kBT. kBT has units of energy. So now none of the terms in that expression have units of energy. Maybe you haven't seen kB, oddly called the Boltzmann constant. What the Boltzmann constant is, I'll write it there. This is the gas constant that you just blew your mind out in the last class, divided by Avogadro's number, right? 8.314 joules per K per mole, divided by Avogadro's number. Avogadro's number gets rid of the mole, and notice that we multiply kB times T. This has units of joules per K. Times K, temperature, is joules, right? kBT is joules. Energy is joules, divided by kBT, joules, no units. And now the expression has no units, which, again, it cannot have units, for all the reasons I just said a minute ago. Now, again, R is 8.314 in standard SI, joules per K per mole. K is in Kelvin. 6.022 times 10 to the 23. Per mole. That's the units of Avogadro's constant. It technically has units of per mole. Isn't that weird? Anyway, and this ends up being a number that you'll have pretty well memorized. So don't worry about memorizing stuff. I mean, you're going to memorize it because you're not going to be able to help yourself. But it'll be on the test. I don't expect you to memorize numbers. That's absurd. It'll be in your calculator. Okay, so this is the Boltzmann constant if you haven't seen it before. It's pretty straightforward. All right, so with that said, I've got just a few minutes left. Let's see. So this is the formula. This is the Boltzmann constant, the Boltzmann formula for probability distribution of energy. And this is what we integrate. And when we integrate things, you can figure out what the probability is that something has some energy. Or no energy, which is 1. I've just answered the question, actually. All right, so to make this a little bit more real, we have to do something with this. I can see a math expression. I like the top part, e to the energy, e to the minus energy divided by a constant. That I think I can deal with. I can integrate that too. But this bottom one, this sum, ew, I'm not sure what to do with that. Plus, what kind of energy? I mentioned translation energy a little bit before. And translation energy is 1/2 mv squared. So I'm thinking about plugging in 1/2 mv squared. And then we can talk about, instead of energy, we can talk about velocity. And that would be kind of useful because you can figure out things. I'm going to tell you what you're going to figure out. So I already know the answer. If I do this, if I change the probability distribution to that of velocity, and I've told you already how to do this, you simply plug in 1/2 mv squared wherever you see energy. And that means on the denominator you have 2 kBT. And then you divide by the sum of the exact same thing. mv squared over 2 kBT. Sorry if that's not big enough. Check the textbook. Hopefully you can see that. I'll be digitally enhancing the video so it'll be readable. Okay, so this is the probability distribution, the Boltzmann probability distribution for velocity, for the velocity of a molecule, of a gas. Let's choose argon. That way we don't have to worry about it rotating or vibrating. Argon can only translate. And the translational energy is 1/2 mv squared. So, and this is Maxwell's contribution. Boltzmann came up with this. Maxwell inserted 1/2 mv squared. Right, so that's why it's the Maxwell-Boltzmann. All right, so there's this. Now this, we're going to analyze in the next class. And we're going to be able to figure out things. This is what I was going to tell you until I went off on a weird tangent. You can figure out things like how fast is a gas moving? How fast is that argon moving on average? Okay, here's a real good one. Now this blows my mind. Can a gas move faster than the speed of sound? If you want a college degree, you're going to come out of here with a college degree in physical science. It seems like that should be something you should be able to answer. Does a gas move, can a gas molecule move faster than the speed of sound? Get this, and this blows my mind. I've been doing this for years. A gas molecule can move faster than the speed of sound. Swear to God. We're going to prove that next class or the class after. Anyway, we're going to do it soon. And we're going to do that using this. We can figure out the average velocity. We can plot what the probability is that a gas is moving with a certain velocity, including that which is faster than the speed of sound. I guess it can technically move faster than the speed of light, but now I'm on a tangent. Anyway, all right, so that is for the next class. I see that I've run out of time. It looks like I've actually used up the full 50 minutes. I'll try not to do that from now on. And I hope this has been fun. And we're on our, remember, only 44 more hours to go. This will go by in a split. And email me if you have any questions. I haven't quite figured out how we're going to do office hours yet, but anyway, hey, vaccines, right? Cool. Okay, so with that, I will see you in the next class. I got something to do here, and I will see you all.